So in a moment, we'll spend about 20 minutes writing the core of Async IO from scratch for fun. But first, I need to talk to you about something more important. This is me. I am GD2K on Twitter, GitHub, and pretty much everywhere else for reasons that aren't as interesting as you might imagine. My real name is Mark Smith, and I'm a developer advocate at Nexmo. Nexmo is a subsidiary of Vonage. We provide REST-based APIs that allow web developers to write code that sends text messages, makes voice calls, sends messages via different instant messaging platforms, or allows you to add video, audio, or chat to your web and mobile applications. If that sounds interesting, we're a sponsor of the conference. Come see us at the booth, stick some bling to your badge, and get a discount code. So I'm currently in the process of adding Async IO support to our Python client library. And it started to dawn on me that I didn't really understand how things worked under the hood. So I went and dived into the Async IO source code, which is 8,000 lines of code. It's reasonably complicated, and after reading it, I realized I still didn't really understand it. So if we're going to write the core of Async IO from scratch in about 20 minutes, we should probably start with a non-agenda, so things we're not going to do. So first, we are not going to have thread safety. We are not going to have exception handling. We are not going to allow features to be cancelled. We're not going to have any validation. We're not going to have any stack reconstruction. No nice debugging capabilities like you get in Async IO. No clever scheduling for scheduling tasks at some point in the future. And we're not going to actually look at any code for I/O, although I will describe how that works towards the end at a high level. So hopefully, this is going to be a nightmare to work with. You would never actually want to write production code based on this library, because it's not going to help you out in any way. But we should at least see how the building blocks go together. So before I get into the low-level details of how Async IO actually works, we should probably recap what some asynchronous code looks like. So just as a relatively straightforward example, here is a main coroutine. We know it's a coroutine because we're using the async keyword in the definition. Inside, we have one line of code which is running another coroutine called gather, which takes a bunch of coroutines, in this case fetch, which isn't implemented here, and it runs them concurrently. And then when they've all completed, whenever that might be, gather will then return and the main coroutine will end. Because main is a coroutine, we need to get hold of an event loop to run it. We can't just call it like we can a normal function. So the last two lines of code are just getting the current event loop, passing the coroutine to it, and then allowing it to run. So the output looks something like this. We have 4 fetch lines. Those are executed in the order that we asked Gather to execute the requests. But because web servers take a little bit, take different times to respond, the responses came in a different order, but they were processed in a different order. So this is kind of evidence that this is actually working asynchronously when you pass coroutines to Gather. Now, we can't implement, well, we could implement our own keywords in Python, but that would take longer than 20 minutes. So we're going to go back to Python 3.4, before the async and await keywords were added to Python. And here, we replace the async keyword with our coroutine function decorator. And inside, instead of using await, we use yield from, because this form of concurrency was built on iterators, coroutines. So we're going to start getting into how you might take some iterators and put them together to make your own Async IO. Because the name Async IO is already taken, I'm going to call my library MySyncIO, because it's not just any Sync IO. Mine is a better replacement for Async IO because it's much smaller and simpler to understand. So let's start with our event loop. You can't implement Async IO without an event loop. I'm going to build this class up over the next 3 slides, I think. So first, we're going to have our initializer. All this does is set 2 attributes. So we have ready. Ready is conceptually, it's a list of callbacks. So a list of functions that we will want to call in our next run through the event loop. We're using a deck from collections because we're going to be popping things off at the front of the queue, and lists are really inefficient at that. Then we've also got a flag that just says we're not stopping at the moment. We haven't been asked to stop. So then we create a public method called callSoon. that takes a callback, which is a function, essentially, and we just add that to the end of our deck. Then we have run forever. This is another public function, so this is what we'll call when we want the loop to actually start running. It runs in a while true, so conceptually forever. And each time through the loop, it just runs our run once function. And if stopping is set at any point to false, it will just, to true, it will just break, and this function will return. Nothing too complex so far, I hope. So the real meat of our event loop is this run once function. And as you can see, it's not actually very long. So it goes through our list of callbacks. It pops the first one off the list, and then calls it. And then it continues to do this until there are no callbacks left, at which point it essentially returns back to the while true loop in the function before. I've got a time sleep in here. You don't need that. That's just there to allow me to kind of see things happening in order. And finally, I've got a stop method, which just sets that stopping flag to true, which means that the run forever will stop. So all of that code is 18 lines. For our purposes today, this is complete. We won't be changing any of it. I will be adding some methods to it a bit later, but this is all we need for an event loop. And I'll prove it. So using this event loop, which takes callbacks, I can define two callbacks. I've got two functions here, hello and world. And then to run the event loop, I just instantiate it, schedule the two functions to be called, and then we call run forever. And so for the first run through the event loop, it pops off hello and executes it, and then it pops off world and executes it. So the result is just that it calls the two functions in order. Now, in a non-async IO world with one thread, when we're running functions, they run sequentially, so one after the other. And this is not necessarily a problem. This is quite an efficient way to run code. But if in certain situations, if task 2, for example, was some kind of loop that is reading from a socket, or responding to bytes coming in from a network, or checking a GUI to see if somebody has pressed a button, then this isn't really ideal, because while task 1 is running, task 2 is not running, which means you're not responding to events from the GUI, you're not responding to bytes coming in from the network. When you have this kind of code that needs to be responsive all the time, it would be really nice if we could cut up each of these functions and just kind of interleave the blocks together, so you end up with something more like this. So it's taking just as long, it's no more efficient, but we are continuously moving between the two tasks so that we can, if in this case task 2 needs to be run kind of a little bit all the time, and so we can be responsive to the network or the GUI. Now functions are atomic. So when you run this hello function, you get a result back, and that's it. And there's no way to really stop the function at any point and restart it later. Whereas if and that's the result of running that code. Whereas if we have a coroutine, this is a coroutine because it has a yield statement in the middle, we've now effectively broken the execution in two. So when you execute this hello coroutine, it doesn't actually do anything until you hit that first next. So as you start iterating through the coroutine, it starts passing control back and forth between the calling code on the right, the code that's running the coroutine, and the actual coroutine on the left. So when we call next, it yields control into the coroutine, which prints hello. When that yield command is executed, it yields control back to the calling code, so the code on the right-hand side, and we print the dot. And then we yield control using next back into the hello coroutine, which runs to the end now, which means that it will print goodbye, and then it will return the result string back to the calling code on the right-hand side. With a coroutine, when you return a value, it's actually embedded in the stop iteration. So this print unreachable on the right-hand side will not be executed. Instead, what will happen is it will catch the stop iteration, pull out the value, and print it out. And so you get this. I hope you can kind of see that this gives us the ability to jump in and out of this function, which is actually a coroutine, which means that we can write something like an event loop that takes a bunch of these coroutines and just goes through each one of them. Each time you run through the event loop, it will call next on the first coroutine, and then the second coroutine, and then the third coroutine. And whenever stop iteration is caught, it knows that the coroutine is finished, and it can take it out of the event loop and stop scheduling it for execution because it's finished. Now, one of the ideas I want to get across around now is that a yield from is blocking. So this is what we call an await in Python 3.7, Python 3.6. So here I've got a coroutine that just prints out hello 3 times, but it yields each time in between. And while it is yielding, it is effectively blocking the calling coroutine. So the coroutine hello world, which calls hello in the middle, while it continues to just be yielded to, it won't move on to the code that I've highlighted in red here. So the red code won't get executed until the hello coroutine returns. So yielding is essentially a blocking move, and returning is then saying you're finished, and the coroutine can be kind of disposed of. Notice how easy this is to run. So the 3 lines at the bottom in black. The first line creates the hello world coroutine, and then just forever it just keeps on running next on hello world. So the yield from command is really just flattening out the nested coroutines into this top level iterator. So you just keep calling next, and each block of code will then be executed in turn. And the result is something like this. So it prints the green stuff, then the blue stuff, then the red stuff. So it looks like blocking code, but each time it's yielding to the event loop, and the event loop can do other stuff in the meantime, whatever it considers to be important. So a quick note on our coroutine decorator, which I mentioned. We're not using the async keyword anymore. So the coroutine decorator in Async IO does a bunch of things around validation. So it makes sure you're passing the right things in. It makes sure you're yielding at the right point. It makes sure you're actually driving the coroutine in the correct way. It stops you from making silly mistakes. And I told you at the start that we're not doing any of that. So in this case, my coroutine decorator does literally nothing, and it just returns the function. But it's a helpful tag at the start of a coroutine definition to just say this is considered a coroutine. So it makes the code look a little bit more normal. And here's an example. So here's how you could implement sleep in MySync IO. So this isn't quite the same as the way Async IO does it, because Async IO has some extra features, but it's a nice illustration of how yielding is a blocking move. So in this sleep coroutine, it takes the number of seconds you want to sleep for. The first thing it does is it calculates when in time it should stop yielding, and then it just, every time it's driven by the event loop, so every time it's yielding, it just checks the current time against the time it should finish. And if you haven't reached that time yet, it continues to yield because it blocks until that point. And then eventually it returns to allow control to pass to the calling coroutine again. And I've just realized I'm going to have to click through a bunch of arrows because I had those lines highlighted. So the problem we have at the moment is that we have this event loop that takes callbacks and executes each one once and then just kind of disposes of it. And then we have coroutines where you need to continue to keep them in the event loop and call next on them until they're finished. Then coroutine is not the same as a callback. They're just fundamentally different things. So if we want our event loop that I told you I don't want to modify, if we want that to continue to work with coroutines, we need to write some sort of adapter to adapt the apples to the oranges. So we put the coroutine inside a wrapper that has a callback method that we can schedule in our event loop. So first I'm going to define this construct, which you may have come across before, called a future. In Async IO, it's considered a low-level construct, so you wouldn't generally write this unless you were writing some sort of Async IO library, something low-level. But it's not just useful, it's essential to the way that Async IO works behind the scenes. The code is not complex, but the concept is a little bit complex. So I'll make sure that I'm going to attempt to explain it as best I can. So first, the future has 2 states. So it's just a wrapper for a value that hasn't been generated yet. So when we create it, we give it a state of pending, which means it doesn't currently have a value. It will do in the future. And we just store away the loop because that may be useful in the future. We have a done method, which just checks whether it's still pending. It just tells you whether it's done or not. And then we have set result, which changes the state to finished and it just stores away the result that's actually been generated, so that any code that wants that result can now get hold of it, now that it's done. And then this is kind of the clever bit, but I also think it's the thing that can be a little bit difficult to understand. So we've got this idea of iterators that we yield on, blocking code until they're finished. Well, that's exactly what this is. So this allows a future object to be awaited or yielded from, and it continues to yield. You'll notice it's like the sleep coroutine we just defined, but it continues to yield until it has a value. So it's testing it whether it's done or not each time. And so when some code from outside of here sets a result, the state changes, done returns true, and then it will return the result to the calling code. So we're still, again, although I keep using words like blocking, we're not blocking anything. We're just continuing to run this coroutine until we actually have a value, and then passing control to the coroutine above. So now we get to the bit that actually allows us to adapt coroutines to callbacks. And again, building on a sort of relatively complex idea, doing it again, but again with relatively straightforward code, not too much. So this is all of our task. A task is a specific type of feature that wraps a coroutine. So this is the thing that maps our coroutine to a callback. So if we look, so you can see it extends future. So it has this idea of you can wait on it for a value. It takes a coroutine when you initialize it, and stores it away for future use. And then this is the important thing. With that event loop, it schedules itself to be called in the future. So we have this step method, which I'm going to go into in a second, and it just says, the next time you run through the event loop, I want you to call me. And this is the method that will be called. So this method progresses the coroutine that you're wrapping, so it moves that on one step. And then when you call next on a coroutine, it has two options. Well, actually, it can raise an exception, but we're not handling exceptions. So it can either return a value, in which case we're finished. So this wrapper is also finished. We don't need to call next on it anymore. We don't need to schedule it for future runs. What we do need to do is set the result on ourselves so that anything that's waiting on this task now gets a value. So we've got this callback that's, it's just a wrapper around a coroutine that can schedule itself in a loop. However, if the coroutine that we're wrapping hasn't finished, then we want to continue to call next on it, which means we need to schedule it for the next run through the event loop. So we just run this line again, like we did in the initializer. And that's it. That's basically what we need to map coroutines to callbacks. So we now have an event loop that can handle both. Which becomes quite important, but I'll explain that in a moment. Because we now have a task and a future, we create these top-level functions in our event loop. All they do is instantiate a future or a task, respectively, and make sure that this instance of loop is attached to them, so that they can. So in the case of task, it can schedule itself to be run. And so we really do have the core of Async IO implemented now, in the same way as Async IO implements it. So if we try this out, this is code that I adapted from the Python documentation on Async IO. We have this coroutine called setAfter. It should really be called returnAfter, and it just sleeps for a delay that you pass in and then returns a value at the end. We need to run this as a task, so because that's how we run coroutines in our event loop. And so in our main coroutine, it's just creating a task around this coroutine, which is configured with a 1 second delay, and it will return the words world. And then we immediately drop into printing hello, and then we can wait for the task to complete. So the task is going to take 1 second to complete. And so we can do this awaiting yielding from the task. And when that eventually completes, we'll get a value back, which will be this world string, and then it prints out. So this prints out hello, and then waits a second, and then prints world. I admit it's a very complicated way of doing that. We can make it more complicated. So using futures as well. This is actually, I didn't even adapt this from the documentation. This is documentation from Python. So here we've got set after, instead of returning the value at the end, it takes a future and then just tells that future what the value is when it's finished sleeping. And the way that we use this in our main coroutine is that we create the future. Future's not attached to anything. It doesn't really have any idea of things that will be executed. It's just a thing that you can wait on for a value. And then we pass it into the task. The task is a thing that's going to set the value. And then we print hello, because I don't know why I'm a bit stuck on this whole hello world example. And then this time we wait on the future instead of waiting on the task. So the task tells the future what the value is, and the future then kind of wakes up and yields control back to the calling code, which in this case is this print statement. So this works the same way as before. The reason this could be useful is because you can have a task that actually fires events at various different points. You know, it emits various values, and you can have a future representing each one of those. So whether it's the task is complete or has raised an exception or whatever. So you can have multiple futures per task if that's useful to you. So the question is why? When I first implemented an event loop in Python, it just took coroutines. It took me 20 minutes to live code it, and it was a lot simpler than this. So it is important to explain why. And the answer is because of the I/O in Async IO. The whole purpose of Async IO is to be able to write efficient asynchronous code that does a lot of I/O. And I/O is done by the kernel, essentially. So when you want to read from a file or you want to read bytes from a network socket, you actually ask the kernel to do that. And it goes away and it does stuff behind the scenes. The hardware and the operating system are essentially event-based. So we need to have an event-based, we need to handle callbacks from the operating system. And the way that Async IO really handles this is to use select. So if anybody hasn't encountered select before, select is a way of passing a bunch of file handles, sockets and things like that, basically IO primitives, to the kernel and saying, are any of these ready right now? Are they ready to be read from? Are they ready to be written to? So if I do this now, will it be non-blocking? So if we call it with a list of handles, which can be files and sockets and things, and it just returns us a new list of just those that are ready right now for that operation. It looks a bit like that. It's a really ugly diagram. I won't explain it. So select is more like a select is not generally used now because it's not hugely efficient. Time has moved on since select was really popular. Nowadays we tend to use other libraries that integrate with the kernel on different operating systems. We have KQ, epoll, proactor, and devpoll on different platforms. Python makes all these available through the select module. And the way, behind the scenes, the way Async IO works with IO is each time through the event loop, it calls, each time you create a socket or a file handle through your event loop, it registers that with the event loop. And then each time you run through the event loop, it calls select with those handles to just find out which ones are ready. And if any that are ready, it schedules a callback for this time through the event loop to just kind of deal with that file handle. So in the case of a reader, it just copies some bytes from that socket into a byte array, and then it awakes a future. So when you're awaiting on read, there's a future behind the scenes that's being waited on internally, and when that's woken up, read will return with a bunch of bytes, hopefully, and your code will continue, while still continuing to be completely asynchronous and working with I/O efficiently. So I won't subject you to any more Async IO implementation. There is a lot more in Async IO, but that really is the core. Everything is really built on that. The actual official implementations are really long because they're dealing with some quite complex stuff like thread safety and exceptions and debugging and stack traces. Yeah, this is definitely, this is literally how Async IO works. And so hopefully kind of will help understand what's going on behind the scenes. If you're interested in the slides or the code, it's all available online. I won't be taking questions right now, but I will be over at the Nexmo booth most of the rest of the day. Or if you don't want to talk to me in person, send me a tweet. My Twitter handle is GD2K. Thank you very much.